speaker of this afternoon session is Madaule from Toulouse, and the title has changed a little bit. It's now Continuity Estimates for the Complex Cascade.
Okay, thank you. First of all, I want to thank the organizer to inviting me to this nice conference and give me the opportunity to present my work today. So I will discuss with you on a work written in collaboration with Rémi Rode and Vincent Vargas on the complex cascade. And this work is strongly motivated by the introduction by Lacroix, Rode and Vargas of the complex Gaussian multiplicative chaos. So in the first part of my talk, I will present this model. And then I will explain the link between the two, between the complex cascade and the complex chaos, and state our result. And finally, give some element of the proof. So first, few words on the real Gaussian multiplicative chaos. So this is a theory introduced by Kahan in 1985. You consider domain D of Rd and X centered Gaussian log correlated field. That means that the correlation between the field at point X and Y can be written as the logarithm of 1 over the Euclidean distance between X and Y plus g of xy, with g a continuous function on D square. So in the scope of the log correlated field, in dimension 2 you have the Gaussian free field or the massive free field, and in the following we will see the star scale invariant field, which are a field defined in a higher dimension. And the goal of the theory is to give a sense to a random measure defined formally as the exponential of gamma your field X. But of course, you can see that the correlation function have a singularity in the diagonal, and so the field X only exists in the sense of distribution, and so you have a non-trivial difficulty to define properly the exponential of gamma this distribution. So the strategy to overcome this difficulty is the following. You consider a regularization of your field X. You call it X epsilon. So now X epsilon is a smooth Gaussian field. And you consider a sequence of random measure, m gamma epsilon, which integrate the exponential of gamma your approximating field against the Lebesgue measure. And you are looking for a deterministic sequence, C epsilon, such that C epsilon times m epsilon gamma converges to a random object, which we will call m gamma. And the crucial point for the theory is that you can, of course, you have some freedom in the choice of your approximation, and the crucial point is that the limiting object does not depend on the approximation. So in the various situations, we know now that the limiting object does not depend on the approximation chosen. So in the context of in the first work of Kahan, he considered some fields which are of the sigma type. It means that he has a decomposition of the field as a sum of independent smooth field, and so you are in the Martigan setup. But the theory has been extended recently by Robert and Vargas and Duplantier-Sheffield by introducing some convolution of your field X. So now I will state 3 results in the context of scarce-scale invariant fields concerning the existence of the limiting object M gamma. So we say that a field X is star-scale invariant if you can retain the correlation function with this integral shape. So you have K a smooth positive definite function, and if you have such a field, you can see that first your field is invariant by translation, and the variance of x epsilon of x is constant equal to ln of 1 over epsilon. You can check that this field is log correlated, and because of the integral form of the covariance structure, you have an independence between the past and the future, and so the sequence, the following sequence is a positive martingale, and as the variance is constant equal to ln of 1 over epsilon, this sequence is just equal to this sequence of random variable. And so the first result of Karan says us that when gamma is smaller than square root of 2D, then you have a convergence almost sure of this sequence of random measure to a non-null random measure M gamma, and moreover he has established some property on the limiting object M gamma. For instance, this is a non-atomic measure and other property. And now when gamma is equal to square root of 2D, you are in the critical regime, and Duplantier, Rod, Sheffield, and Gebergas have proven that you need this time to multiply your random object by an additional square root of ln of 1 over epsilon, square root of the variance, in order to have convergence in probability to a limiting measure, which I denoted M prime, and which is called the derivative random measure. And finally, when gamma is bigger than square root of 2D, you have now a different normalization, and you have a convergence in law. And the important point here is that the normalization makes appear a term to the power 3 gamma half, and it is related to the study of the extrema of the approximating field. So it is related, for instance, to the study of the extrema of the Gaussian free field. Okay, so now I can introduce you the complex chaos. So you have your log correlated field X on RD, and you consider Y an independent copy of X, and Y epsilon is a regularization of Y. And now you are looking for the measure. You want to study the sequence of complex random measure M gamma beta. You have 2 parameters defined as the exponential of gamma, the real part of your field, plus E beta, the imaginary part of your field. And again, you want to find the good way to normalize this random object in order to have a non-trivial limit. So in the paper of Lacroix, Rand, and Vargas, they have obtained this fast transition diagram. I will produce it on the blackboard. So you have 3 phases. First, you can see that when beta is equal to 0, you are on the line here, and you recover the transition phase at gamma equal to square root of 2D. So in their paper, they have studied most of the three phases. In phase 3, they have obtained a convergence in low to complex white noise, and this result is also true for the frontier between phase 1 and 3 and 2 and 3. In phase 2, there is for the moment, no result, but it is conjectured that you will obtain in the limit an atomic measure, and again, when for the large value of gamma, obtain a result in the phase 2 will involve to known the extremal particle of your Gaussian field. And in the phase 1, basically for the small value of gamma, you have the following result. So this is also true for the frontier between the phase 1 and the phase 2. So you take gamma and beta in these phases, and they have proven that for any compactly supported function phi, the martingale, which is the integral of your function phi against the exponential of your complex fields, normalized by this term, which is exactly 1 over the expectation of exponential gamma x epsilon x plus e beta y epsilon x. You have convergence almost sure and in L1 to a random variable denoted by m gamma beta. Okay, so we will in the following interested in this result, but first I want to try to give two motivation to study the complex chaos. The first one is I will try to make a connection between this model and the Sine-Gordon model. This is so the Sine-Gordon model in dimension 2 is you consider a domain D of R2, and you want to define a field Y under the following action. So you have two terms, one which involves the square of the gradient of your field, and another one which is mu times the integral of the cosinus beta of your field Y. And it is well known that these terms is exactly the terms which gives you a Gaussian free field. And so if you want to define a field Y under the Sine-Gordon model, you take a functional f of your file Y. It will appear as a limit when epsilon goes to 0 of the expectation of f y epsilon. Y epsilon is the approximation of your field Y times the exponential of minus mu times this term which involves the cosinus. And of course, the cosinus of beta y epsilon is just the real part of your Gaussian chaos. So if you want to define properly this field Y, you first need to show that this quantity admits a limit when epsilon goes to 0. So actually in physical literature, there is already a result on gamma for gamma equal to 0. I mentioned in a paper of Froelich, and but while it gives a connection with a well-known model, and you can also see you can also make appear this Gaussian chaos when gamma is equal to 0. If you look at the charge of Coulomb gas, and you will see that the correlation between the charge at 2 points will appear, will be in the limit when the mesh of your lattice goes to 0, will give this expression. And again, you have the real part of your complex chaos. So now in the following, we will we will be interested in what happened in the frontier between the phase 1 and the phase 2. And one on the important property of the limiting object m gamma beta in this frontier is its property of conformal invariance. Indeed, if you take a field xy which satisfies this identity law, one can show that so you have a conformal map C between two domain D and D tilde, and you can show that if gamma and beta are equal to 2, so this is in dimension 2, the limiting object m gamma beta is conformally invariant. And so it will be make this field, which is called the tachyon field, as a building block for the Coulomb gas on a random lattice. Okay, so now I will explain what interested us in the following. So I have restated the result of Lacroix-Rodenbach gas in the frontier between the phase 1 and the phase 2. And we can restate it like this. For any t on Rd, the sequence of random variable, so you have the same normalization, and you take the weight given by the complex random measure of the product of segment 0t1, 0td. And you know that this sequence converges most surely and in L1 to a non-trivial limit m gamma beta. And our aim in this work is to establish a continuity result on the function which maps t to m gamma beta of 0t1, 0td. So, we have not obtained this result for the complex chaos, but we have obtained this result for the complex multiplicative cascade. So, I will present now what is the complex cascade. So, this is a random field on the tree. So, you have a binary tree T, and to each vertices of the tree, you will associate a real position V of z and an imaginary position x of z. So V and x are independent, and the way to choose the law of V is the following. You first consider an IID sequence of Gaussian random variable theta u and gamma u associated to each vertices of the tree, except the root, and then you say that the position of V, the real part of the position of z, V of z, is equal to the sum of all the theta u for u belonging to the direct path linking the root to the vertex z. So V of z, here we are at generation 4. So the absolute value of z is equal to 4, and V of z is the sum of theta subscript z of 1, which z of 1 is the ancestor of z at generation 1, plus theta z2, with z of 2 the ancestor of z at generation 2, plus theta z3 and theta z3 here, and theta z4. And you do the same for the imaginary part with random variable gamma. Now it remains to choose the law of the random variable theta and gamma, and we have chosen in order to make easily the comparison with the complex chaos, we have chosen for the law of gamma this random variable, and for the law of theta, you have now a drift of 2 ln of 2. So first, what is the link with the complex chaos? The link relies on the fact that the complex cascade can be seen and as a log correlated model on the tree. Indeed, if you take two vertices x and y in the tree T at generation n, you can define the distance between x and y as 2 to the power minus large n, with large n which is the generation of the youngest ancestor of x and y. So this is very simple. You have your tree. So maybe y is here, x is here. And so you look at the youngest ancestor of x as y. This is the vertex u here. And so the distance between x and y is equal to 2 to the power minus the generation of u, which is here 1. And if you do that, it is plain to check that the covariance of the real part of the field is between two vertices x and y is exactly equal to 2 times the logarithm of 1 over the distance between x and y, and you have the same relation for the imaginary part. And so this important observation makes the cascade as an archetype of the Gaussian log correlated models, and it is now known that a large class of results are valid for many log correlated models. And so in this view, prove a result for the complex cascade is the first good step in order to prove the result for the complex chaos. So to end this analogy between the two models, it remains to define what is the analog of m gamma beta epsilon in the context of the cascade. So you can naturally put in bijection the set of vertices at generation n and 0, 1 to the power n. You can encode every vertices of the tree in the following way. So you take a vertices u, and you look at the path linking the root to the vertex u. And first you see that you go to the left. So the first coordinate of u is 0. Then you go to the right. So the second coordinate is equal to 1. Again right, 1, and finally 0. And then you can associate to each vertex u of the tree a real number t of u, which is simply the dyadic real number associated to this vector. So you sum between 1 and the generation of u, u subtract e divided by 2 to the power e. And now the definition of m gamma beta is the following. So this is a complex random measure absolutely continuous against the Lebesgue measure, and you sum every particle at the generation n. You put the weight of each of these particles, which is the exponential of gamma minus gamma, your real field, plus e beta, your imaginary field, times the indicator function that x is in the segment tu plus 2 to the power minus the generation of u, and you normalize it by 2 to the power n. Okay, so what do we know about this complex random measure m gamma beta? In fact, we already know a lot when when beta is equal to 0. So when beta is equal to 0, you only have the real part of your complex cascade. So this is simply a cascade. This is also called a branching round walk. And as I have chosen the law of the position of the real part like this, we can check that the branching random walk is critical. So it means that we have the two following relation. And when we have the two following relation, we know the three following results on the behavior of the sequence of random variable m gamma. So the first result due to begins tell us that when gamma is smaller than 1, m gamma divided by its expectation converges almost surely to a random measure, non-null random measure, a non-null random variable m gamma. When gamma is equal to 1, you are in the critical case, and now you have convergence in probability, and you need now to normalize your random variable by the square root of n. And finally, when gamma is bigger than 1, you have only convergence in law, and you find again this n to the power 3/2 times gamma. And again, it is related to the behavior of the extremal of the branching random walk. So you can see that this is a perfect analog with the three previous results that I have stated at the beginning of my talk. And so we will, I think now, not be surprised if I tell us that, if I tell you that the fast transition diagram for the complex object m gamma beta is now the following. So you see that this is exactly the same fast transition diagram, except that the critical value is not square root of 2d anymore, but 1. So this is just because you are now in dimension 1, and because also you see that when I define the complex cascade, you have here an additional coefficient 2, and so it makes just a little bit change the position of the frontier. Okay, so as I said, we are interested in the behavior of the limiting object obtained here in the frontier between the phase 1 and the phase 2. So before to state our result, I should say that there is two previous work on the complex cascade. The first one is due to Derrida, Evans, and Spear in 1993. And in this paper, they have studied 1/n the logarithm of the modulus of mn gamma beta, and they have obtained this fast transition diagram. But of course, they have not the existence of the limiting object. In 2010, Barral, Jean, and Mandelbrot has make a very similar study. They studied the regularity of m gamma beta when gamma beta are in the phase 1, so inside in the inner phase 1. Okay, so in the context of the complex cascade, we know that on the frontier 1, 2, for any a, b belonging to 0, 1, the complex martingale Mn gamma beta of the segment AB converge almost surely and in L1. And now we would like to define the maps which associate T to M gamma beta of the segment 0T as a continuous function. And so our result is the following. So in the frontier 1, 2, the sequence of a continuous function which maps T to Mn gamma beta of 0T converges almost surely in the space of continuous function. And moreover, we have an estimation on the modulus of continuity of the limiting complex measure M gamma beta. For almost sure omega, there exists a constant which depends on omega, such that for any st in 0, 1, the modulus of M gamma beta of st is smaller than this constant divided by the logarithm of 1 over the distance between t and s to the power xi gamma. So the constant xi is not optimal in our work. We will see in the following that we think that this optimal xi should be 1/2. And you see that the regularity of the limiting object depends on the parameter gamma. So more you are close to this point, more you are regular. So in the remaining time, I will try to give you some elements to prove this result. And the first approach to try to obtain this result is first to obtain a lower bound for the modulus of continuity. So we want to study such type of quantity. So you have L belonging to the integer, and you want to have a control on this quantity. So, and the first thing that you can do is to look at this at the modulus of continuity of M gamma beta, but restricted to the dyadic interval. It means that you simply observe that this supremum is smaller than, bigger, than the supremum for U belonging to the tree, U at generation bigger than L of M gamma beta n of the interval tu plus 2 to the power minus u. Okay? So it just means that if you are in the tree, you have here the generation L, you are here at generation N, and you only look at the point S and T such that okay, I will make a proper drawing. Okay. You only look at the S and T such that S and T are the extremity of one subtree of the tree T. So here, for instance, if S corresponds to this vertex and T to this one, you see that they have a U for common ancestor, and so the interval ST is equal to TU plus 2 to the power minus U. Okay? And the very convenient fact to this type of amount is that you can decompose it as a product of first the exponential of the field at the vertex U times m gamma beta n of U, which is this random variable, and which is the mass of the subtree rooted at U. And because of the branching property, these two random variables are independent. And of course, you can have also this identity when n goes to infinity. So we will see now how we can obtain a lower bound for the modulus of continuity. So you take L large, and you want to find the constant xi such that this quantity converge or not to 0. So this probability, as I explained, is bigger than this one. So you restrict yourself to the dyadic interval. Now you use the identity. Because of the modulus, the complex part disappears. And now you see that to understand this probability, you need to understand the position of V of U. And there is a nice result of Heidecon and Shi in 2014 in their paper on the Seneta-Hyde norming, which says that with a non-null probability, when n goes to infinity, there exists a vertex U such that V of U is more or less equal to 1/2 times the logarithm of n. So regarding if you look only at the real part of the branching random walk, as I said, the branching random walk is critical, and we know in this case that if you look at the minimum Mn of all the positions at generation n of your branching random walk, we know that by Eli Heidecon that Mn minus 3/2 times log n converges in law. But if you look at the almost sure behavior of the minimum Mn, you see that you have a fluctuation, and there exists and it will happen that some vertex will be at the position 1/2 times log n. So if you place yourself on this event, and because of the independence between this guy and this guy, you have more or less this inequality, and so you can see that you have the probability that m gamma beta u star with u star this vertex such that V of u star is equal to 1/2 times log n, log L here, bigger than this quantity. And you see that if xi is bigger than 1/2, if you see that if xi is bigger than 1/2, this quantity goes to 0, and as m gamma beta u star is distributed as the same distribution as m gamma beta, you have no chance to obtain convergence of this probability to 0. So for this reason, we know that C is necessarily smaller than 1/2. Okay, so now we want to obtain an upper bound on the modulus of continuity. And we want to study this type of quantity. And of course, we can no longer restrict ourselves to the dyadic interval St. When you are in this case, you are in the case where you have a dyadic interval, because you have here one ancestor, and the set of red vertices form a subtree. But you can be in this situation where you do not have this nice decomposition that I have expressed here. So, in fact, to bound this quantity, we will need to understand this function. So you want to understand the function t, which associates m gamma beta of the interval 0t. Okay, if I zoom what happens in the subtree, in this subtree, and I say that this vertex is now the root, I see that I need to bound the maximum of this function when t goes from this point to this one. And now if I denote it by m gamma beta infinity, the supremum for t belonging to 0, 1 of m gamma beta 0t. You can see that the modulus of continuity of m gamma beta at the scale 2 to the power minus g is smaller than 3 times the supremum under all the particles at generation g times exponential minus gamma v of u. So this is here the real weight of each vertex here, times m gamma beta n u, where m gamma beta n u is a random variable distributed as m gamma beta here, but which is independent for different vertices u. And now the cornerstone of our proof is to obtain a result on the tail distribution of this random variable m gamma beta. So this is the proposition star. It says that there exists a constant c and eta strictly smaller than 1, such that for any x bigger than 0 and n integer, the probability of this supremum m gamma beta is bigger than exponential of gamma x is smaller than exponential minus x times this polynomial part. So you see here that the tail distribution of m gamma beta depends on the parameter gamma. And in order to improve our result, we should show that this result is true for every eta smaller than 1. we should true that this result is true for any small eta bigger than 0. So now I will explain how to obtain the continuity of m gamma beta from this proposition. So this is a very classical computation in the context of branching random walk. So you want to prove that the probability of this event goes to 0 when g goes to infinity. So you fix epsilon and you look at the interval st such that t minus s is smaller than 2 to the power minus g. Because of the inequality here, I can bound this property by this event. So I make appear the random variable m gamma beta infinity. And now we are again in the favorable situation where m gamma beta of u is independent of exponential of minus gamma v of u because of the branching property of the tree. So you say that the probability of the supremum is bigger than something is 1 minus the probability of the supremum smaller than something. And then you condition to what happens in the tree before the generation L and use the independence between the different random variable m gamma beta of u. And now you see that you have to deal with the probability of m gamma beta infinity bigger than exponential gamma v of u. And we know that the real part of the complex cascade in the because the real part goes to infinity. It goes to the vitesse to the speed 3/2 times log n. So you can see that this guy here is large, and now you can use your estimation on the tail distribution of this random variable. Okay, so it make appears v of u to the power eta, and eta is smaller than 1. And now we want to prevent from the bad event where there exists a particle u such that v of u is very small, but we know that the infimum of the branching random walk goes to infinity, so we know that all the particles v of u are bigger than minus infinity. So at epsilon, with loss epsilon, we can place ourselves on the set omega minus b, which is a set where all the particles v of u are bigger than minus b. And then you use a trivial inequality. 1 minus exponential of x is smaller than x. And so you have to deal with this expectation. And you see that I have added the indicator function that every particle is bigger than minus b. And now you have finished, because this amount is computable. By the many-to-one lemma, you can say that this amount is equal to the expectation of 1 plus sg to the power eta times the indicator function of the random walk sk is always bigger than the level minus b, and it is easy to see that for such a random walk with a second moment, this quantity goes to 0 when g goes to infinity. And so it gives you the continuity of the limiting object m gamma beta. Okay, so to conclude this talk, you see that to understand the modulus of continuity of m gamma beta, you only have to prove that m gamma beta is a bounded function. And if you have that, if you can prove that m gamma beta is a bounded function, and if you have estimate on the tail distribution of the supremum of this function, you can have, because of the tree structure, the estimation on the modulus of continuity. So I will end it. Thank you for your attention.
Just a comment. I think in the real case, there were results by Madaule and Christian Webb and a few other Finnish guys that obtained also upper bounds on the modulus of continuity.
Yes.
Critical cascade.
Yes, they obtained. So they obtained, I think. So in for the real case, they obtain here a constant equal to 1/2. So there is psi gamma have to be replaced by 1/2. So if gamma goes to 1, you have a continuity in the property of the continuity of the m gamma beta and what happens in the real critical point.
So the two results match up in the case of the
real case.
In the real case.
Yeah.
And is this just an upper bound, or is it also a lower bound on the modulus of continuity? Is that basically really the answer?
Yes, I think this is really the answer. Yeah. I remember that they proved that it cannot be more regular than 1/2 in the paper.
Just with regard to maybe computing these these probability distributions that you're, have you thought of using? Is there any way you can? Because you said you've got a martingale halfway through, right?
Yeah.
And then you're looking at the supremum of these sequences of martingales.
Yeah.
Is there a way you can derive like a stochastic equation or anything for these martingale processes, and then work out the probability distribution from that? I was just thinking, is there any way, when you're taking the supremum over the vertices, right?
Yeah.
So
This is not a martingale.
no, but in order to calculate these probabilities, can you not like derive a kind of probability distribution for the supremum of those variables somehow? I mean, you can't work out a stochastic equation for the. I mean, just order the vertices, right?
Mm-hmm.
And then think of it as like a process evolving in time, but with the vertices as like the steps.
Yeah.
And then to work out the supremum, maybe you can derive like a kind of difference equation, if you like, for the a stochastic equation. Do you know what I mean? But a discrete version. So in terms of the difference of the supremums, maybe, or because then you can use this Fokker-Planck equation to just derive the probability distribution. It just seems to work in a lot of cases, you know, with these types of processes. And also this martingale representation theorem, you know. If you have a martingale, you can represent it as a stochastic integral.
Yeah.
So just the idea is that you're generalizing this. Can you represent it as a sum of a stochastic integral and just another? I mean, in other words, can you derive a stochastic equation for the?
We not succeed to derive a stochastic equation for this function m gamma beta of 0t.
Yeah, right. I think it's interesting to.
The difficulty here is that if you are in the real case, of course, this function is monotonous, is monotone, and here it's pretty difficult to obtain a bound of this function. But we don't use an equation satisfied by m gamma beta of 0t.
More questions?